Let me introduce Don Thompson. He's Director of Engineering at R&D Altanova. Don started his career at the Teradyne, working there for 11 years, designing high-speed instrument interface, and has now spent nearly 20 years as a signal integrity expert in the ATE industry. He leads a team of more than 100 engineers designing and building the most challenged ATE interfaces for the industry, leading customers around the world. Thank you, Don. Go ahead.
Thank you. Let me start off and set the stage to get into this discussion. So R&D Altanova is a PCB manufacturer. So we build load boards, probe cards, and basically the glue that connects the testers that we've just been talking about to the sockets and ICs that need to be tested. So that's the context that I'm approaching this discussion in. It's really looking very specifically at the PCB side of things. How do we take the PCB and optimize it for the challenges that we're seeing within the 5G space? So the biggest, most glaring challenge, of course, is the increase in frequency. Jumping from a 5 gigahertz signal to a 40 or 28 gigahertz signal is a significant challenge. So there's all the difficulties that go into upping that frequency range from something that was relatively mundane to something that is very challenging and poses a lot of issues, especially as you start looking towards higher site counts, higher volumes, and better quality. And then you couple that in the 5G space with beamforming multiband radios, and now you have additional RF channels per DUT, and the PC board wants to be able to deal with those channels appropriately. Now, a lot of the presentations we've seen so far today, coming from the tester side, you look at solutions and they've got a lot of cables coming off of them. And that has been the go-to solution, especially early in the 5G test realm, is let's solve things by putting in RF cables, right? Now, that's great for quality. It has a low loss solution, but it poses volume challenges, right? Going to high site counts, going to high tester counts, you end up putting a lot of money into cables, which also are not terribly reliable, right? You have to make sure everything's torqued correctly. If anyone, drops something on a cable, you could have a very challenging to debug issue. So there's lots of reasons why, as you move into the 5G market as a mature market, you want to be moving more and more towards PCB solutions, if at all possible, right? So it also, again, from a high volume, from a high site count side, additionally, you don't really want to have 100 cables on a board. That's a ton of money and a ton of complexity, and somebody has to assemble those, build those, test those, phase match those, blah, blah, blah. All right. You also have potential for resource sharing. And again, if you can do resource sharing on your load board, as in a MUX or something of that sort, where you can take a single instrument, a single RF lane from the tester, and split it amongst several channels within a single device or several devices, that's going to, again, either make it cheaper to have less instruments on the tester, or cheaper on not having as many cables coming off of the load board. And again, trying to get to scale as you go from, okay, I've got my 3 boards working and now I want to scale to 20 or 40 sites. It's a lot easier to do that in PCBs than it is in cables. So these are some of the challenges and desires for why we're trying to move and and optimize our PCB performance so that we can use it where it's needed and try to solve some of these challenges as 5G starts to go from, introduction to high volume manufacturing. Okay, so what do we really need to provide for this to happen? So the first thing is we really need a best practice guidebook, right? We want to dive into it, and there's a lot of let's call it industry knowledge on the subject. Maybe conventional wisdom. Not all of it is true, but some of it is, and we need to apply some of that to how we can make this successful in this area, given the other constraints within the system, right? And what I mean by that is there's a lot of RF knowledge out there. People have been doing RF at these frequencies for quite a while. And the real challenge is how do we apply that to our environment where we've got our constraints within the ATE environment. So what does that best practice guidebook look like? Part 2 is we have to be extremely reliable in our simulations. So we have to have this very characterized, and we have to be building what we're simulating, right? This is constantly an issue when you're starting to get into these very time critical environments, right? In ATE, we don't have time to spin a board or two if we aren't hitting the right frequency at the right place or with the right loss. We need to have a very high confidence that what we simulate, what we are testing, what we're signing off in the design phase is what's going to be built right out of the gate, because there's just no time to say, all right, let's take another month and spin the board and get it back, and we'll dial in the frequency just a little bit, right? That just is not a function of this market. So that also requires a very reliable fab process. And again, it's a high correlation between the simulation and the fabrication. And so that's both pieces of that, right? That's knowing, having characterized the fab, and having the fab be repeatable. And then, of course, in order for all of that to work, you have to be doing good performance validation. We have to be doing VNA measurements and tracking that control system of simulation to manufacturing. And all of that is very useful so that when we get into doing more advanced things within the load board or probe card, they come out correct, right? The things we want to really be able to do is to build in a balun, to build in a filter, to have a predictable loss on a trace, potentially to do a mux or resource sharing of a device, of an RF line. All of that, if we can put it on the load board, saves us time and money in the overall solution. All right, so let me just make sure we're all familiar with these terms. I mean, this is super basic for any SI engineer out there, but there's a lot of people online. And I'm going to start using these phrases as we look at the data, right? Insertion loss is really how much energy you send out versus how much arrives, right? So if you have 100%, that would be perfect. That never happens. So you always have some percentage of what you're sending out arriving at the other end. Return loss is another facet of this, where you send it out and you're looking at how much comes back. So this is usually in regards to reflections that are causing some of the energy that you're sending out to be coming back at you. And to measure that tells you where some of your energy is going. And if you look at it in the time domain, you get impedance, which tells you potentially where issues are, where reflections are occurring, right? So this is very similar to return loss, except it's in the time domain. And we use it to look at specific locations of where there are challenges and difficulties, whereas return loss doesn't give you location data unless you convert it into impedance. And then isolation is simply just how well are you keeping your signal to noise ratio from other sources down, right? So if you've got multi-site or anything like that, how do you make sure that those other sites aren't doing something on the side and that's causing the site you care about to give you bad data? All right. Now, the first real question is, why is this hard? And as I get into this, there are a couple assumptions here. The first one is really that we're looking at microstrip. And so microstrip is the outer layer of the PCB. And it is a particular challenge to get high quality signals on for an ATE board. And the reason for that, I lay out in this slide. You basically, in the manufacturing process, when you're building the PCB, you start with a very predictable thickness of copper. So in this case, for my example, we're starting with 1/4 ounce copper, so 0.3 mils of copper. And that's coming from a manufacturer. It's very controlled. We can actually get it, you know, as controlled as you want it, more or less. And we start with the very, very consistent copper. And then you go through the process of drilling your vias. So you have to drill vias in the board, and then you plate those vias. And when you plate the vias, you're also plating the outside of the board. So typically the standard rule is you're trying to get a mil of copper on the whole wall of a via. And if you're putting a mil inside the via, you're getting at least a mil on the outside of the via. And this also is not a perfectly even distribution, because a lot of this has to do with the density of the copper in your plating solution, how the voltage is changing throughout the board when you're going through your plating process. There are different reasons, but that leads to the copper on the outside not being terribly predictable. And then when you get to the via itself, you tend to get a knee, so you get a little extra copper. And all that means is you come back in and you have to sand this down. So you're planarizing the outer layers to try to get it smoother. Great, but we went from we're not sure how much copper we're putting on to we're not sure how much copper we just took off. And then we go through all of this again. We have to fill the vias. And in most boards we're doing via and pad. If we're doing via and pad, that means we fill the via and we plate over that so that you end up with a pad that has the via embedded in it, but it's all copper on the outside. So again, we're going to go through another plating operation, and then we have to go through another planarization operation. And this is all before we've even etched the image on the outer layer. So all of this together is really just an exercise in showing that the control of the copper on the outside of these ATE boards is not terribly repeatable. And because the thickness of copper on the outside of the board isn't highly known, that makes dialing in the etching processes also a challenge, because you want to make sure when you etch it, you're etching through the amount of copper that's there, but not over etching it, because that leads to things like undercut, where you're etching underneath your mask and getting rid of more copper than you want to. So this poses a lot of challenges on how you deal with the outer layer of your PCB, and why it's hard to get to high quality microstrips that are repeatable, consistent, board to board, lot to lot, design to design, year to year, etc. And traditionally, PCB shops will only offer impedances on the outer layer at plus minus 10%, whereas internal, it's not a big deal to get to 5%, or in engineering cases, even tighter. All right, so I started with the assumption in that last slide that we were basically looking at the outer layer of the PCB, right? Now, the question is why? So again, putting on your legacy hat of the RF engineers that grew up in the 80s and 90s, the early 2000s, they didn't have access to high quality 3D field solve tools until maybe the late 90s, early 2000s, and they tended to stay away from vias because vias pose a lot of challenges, and without a 3D field solve tool, you do not have a good ability to get into the data and optimize via and make it good enough quality for you to reliably get good performance out of this. So coming at that from the history side, the general rule was you just don't use vias. You just stick it on the outer layer. You have a 2-layer PCB or maybe 4-layer PCB, and you don't do too much. Part 2 is that microstrips will give you a lower loss in a strip line for a given dielectric thickness. And so that just tends to be easier. And if you're not running high density, running it on an outer layer of a PCB is easy. They could get some high quality etch if they're not doing a bunch of vias like we are. And in general, it's a pretty good solution. So from the legacy standpoint, makes a ton of sense. And you get good or potentially better performance than stripline. And part 3 is that even with 3D field solve tools, vias are still hard. And they take more work and they have more risk. And there's more aspects that have to be correct between your PCB fab and your final product, which poses a lot of challenges. So in general, when people are looking at high-speed RF, they're really talking about the outside of your PCB. Now, that doesn't always have to be the case. And depending on the frequency, there are times when density will dictate that you have to go to stripline. But most of this presentation is focused on microstrip because I really haven't seen the market move enough in the direction of looking at strip lines for that to be a serious part of the topic here. Although there's a lot of information, a lot of work we've done on looking at the vias and strip line traces in the probe aspect that makes that part very interesting when we start getting into densities. So let's look at the different trace transmission line structures that we're going to be talking about here in the next couple slides. Right, you've got strip line, which just is inside. You typically have about a balanced ground plane on either side. Microstrip is just a trace on top of a dielectric. So this is going to be on the outer layer of the board with all the challenges we just talked about a minute ago. And then coplanar waveguide, where you have a ground plane that comes up and surrounds the trace as well. And then there are a couple aspects to this. The air gap that you design in is a variable. It doesn't have to be one specific thing. And we're going to look at the variable, how this affects your performance as you look at the transmission line. And then another piece here is going to be the dielectric, which I've really broken up into 4 categories. There's FR4, mid-range, high performance, and Teflon. FR4 is used for cost. Actually, let me talk about that in the next slide. I won't get into that too much here. Okay, I talked about all of that. And again, we like microstrip and CPW because there are no vias, and that makes some things easier. And again, with our boards that are typically 200 thou thick or 5 millimeters, you may end up with some stubs on the vias, or you have to back drill, which has tolerances, etc. So there are challenges as you go internal. So everything's going to be focused on microstrip and CPW. So here's a quick chart showing the different dielectrics that I laid out in the last slide. So FR4 has a very high loss tangent. That means it's a very lossy, loss per inch is very high for an FR4. This is pretty awful, but it's cheap. In our market, that's not interesting enough. I mean, everyone likes cheap, so I'm not trying to say that that's not legitimate, but we're not doing a high enough volume in terms of the FR4 to be interesting. If we're doing 1 million boards, FR4 makes more sense. If we're doing 10 or 20 or 40, it's just not interesting to be here, and we might as well go to a mid-tier like a Nelco 4800-20, and the loss tangent is getting a lot better. And then there are high-end, high-performance dielectrics, which tend to have loss tangents that are down in the 0.003 to 0.0016 range. And these start to be pretty good, and these are a good choice for what we're looking at. And then there are the very high-end dielectrics, which tend to have Teflon as part of the mix, which has some advantages from a loss standpoint, but also makes it hard to stick the board together. You tend to get some DLAM issues with the Teflon. It's a lot bigger of a challenge. So there are more manufacturing issues in the Teflon based. So what I think is most interesting to focus on here is the loss, not so much the dielectric constant, in my opinion. I mean, this is good for giving you a wider trace for a specific dielectric thickness, but it's not super interesting otherwise, whether it's 2.8 or 3.3 or 3. That doesn't really do too much for your overall RF performance. Now, when we actually sit down and do simulations on this data, we can see some significant differences as we compare FR4 to our mid-tier to our high performance. But once we start to get into the high performance in Teflon, we see a point of diminishing returns. So you're really only maybe about a 10% window from the worst high performance to the best Teflon. And you're really getting into, like I said, limited benefits as you start to look at these very high performance dielectrics. So it's really not worth chasing the absolute best dielectric out there. It's better to spend your time looking at the design. How do you shave off a little bit of length? How do you improve your impedances? That tends to be more interesting than trying to knock off the last tenth of loss tangent in your overall design. And again, like I said, as you look at these higher end ones, they get to be a much bigger challenge to manufacture. And if the benefit you get from these is pretty negligible, then it's not worth the extra risk and cost associated with going in that direction. Typically, if you've got a design that's very insertion loss sensitive, then it may make sense. But in most cases, I haven't seen that the benefit outweighs the risk and cost. So when we look at this type of chart, what we're getting out of this is all loss per inch. So if we have 1 inch of FR4 at 14 gigahertz, then we're looking at an insertion loss of negative 0.2 or negative 2 rather. And if we come up here, we're looking at an insertion loss for the higher performance ones, less than 1. So that means we can go twice as far in this for the same loss as FR4, or 2.3 inch for basically 1 inch of FR4. Or for a mid-tier, we could go 1.7 inch for 1 inch of FR4. It gives us the ability to route farther for the same loss. Or potentially the other way to look at it is if I've got an inch of loss, an inch of trace, this is the loss I'm going to get. So you can use this type of chart to calculate how much loss you're going to have for a given set of length of trace and dial it in accordingly. Okay, so let's start talking conventional wisdom. Like, what do we think we know when it comes to transmission line loss? So first off, microstrips are better than strip line. Let me get out the laser pointer. Microstrips are better than strip line. All right, we think we know that. Coplanar waveguide is better than microstrip. Coplanar waveguide tends to be the preferred transmission line for RF engineers. Surface roughness has a significant impact on performance. There are lots of studies on this. The real question is, how does this compare manufacturer to manufacturer? Because each manufacturer gives a number, but they're hard to really compare to each other. So one of the things I want to get out of this set of data, and unfortunately I don't have it in this presentation because some of the test boards were delayed, is how the different manufacturers compare to each other, right? They all have published specs. They all have, on both insertion loss, on both their dielectric constant, their dielectric loss, and their surface roughness. And the real question is, how does that published spec compare to what we actually measure when we build it? Because there's no guarantee they're the same thing, right? We tend to trust that it's all going to be good, but there's an inherent bias on their side to make sure the numbers that they put on their sheet look the best. And if there's a slight error, you know, it's going to probably be in their favor. So basically comparing how the published specs measure against reality. And again, both the surface roughness and dielectric loss. Next, gold wrap should make the microstrips and CPW better. Gold wrap is when you plate around the sides of the transmission line, not just the top, which typically is what you see. Next is nickel may or should have a negative impact on performance. The argument that I have read is more focused on the magnetic properties of nickel rather than the increased resistance that nickel has. Those are the two potential areas where we can get negative performance from nickel. And then next is just a question, does any peg provide a benefit or potentially a negative? Any peg is instead of gold nickel, it uses palladium and immersion gold, which has some advantages elsewhere. But the question is, how does this affect the RF performance? If we can see a benefit, that's great. If we see a negative, we want to understand it and characterize it. And then as we dive into things, the way we do the etching on the outside, there are multiple ways to do it. It's not one solution on its own. And we've looked at several potential options on how we can improve this at RDA. And so we've got a couple options there that we're saying, what if we try this? What if we try that? And we want to see if these have any significant or reasonable benefit, or if they're all, you know, we get the same performance no matter what we do in that case, and the main detractors are other things. And as an extra, how much does the CPW dimensions affect loss? So we're going to look at this a couple slides from now. All right. First is some data looking at microstrip compared to coplanar waveguide. Now, this is a coplanar waveguide, but it is a very tightly coupled CPW. And that was an intentional decision when we selected this CPW. The idea was, if you've got a CPW and you pull this gap in really close, you end up coupling a lot more from your trace to your ground this way than your trace to your ground this way, or at least a lot more than a normal CPW. And if you have your energy going left to right, right here, rather than up and down, then the majority of your energy is not going through the dielectric, and therefore you have an air dielectric in that area. And of course, the only thing better than an air dielectric is a vacuum dielectric, but air is extremely good. And so in theory, if you can push enough of the energy here, then your loss should be lower from a dielectric loss standpoint. However, your skin effect loss may be increasing due to the smaller area that you're forcing the energy into. And that tends to be what we see here, is that the CPW has higher insertion loss, which means it's worse than the microstrip, which in this case tends to be about a 20% improvement over the tightly coupled CPW. So in this case, what we see is that the CPW in the extreme, when we go to a very tightly coupled CPW, it's worse. And a microstrip is better. So potentially somewhere in here, as we go from tightly coupled to loosely coupled, we can find something that works better for a CPW. We also tried doing some gold wrap, where we wrapped gold around the side of the CPW, and we saw pretty negligible performance, tiny bit, but not too significant, and actually a little worse at low frequency and a little better at higher frequency. Next, we've got a couple other experiments here looking at nickel gold versus silver plated. So silver has a lower resistivity than gold, so potentially plating it in silver is better. This is something, again, it's conventional wisdom is that silver plating is going to provide an advantage. In this case, we had the exact same board. We sent one out for silver plating and one we did gold nickel, and we saw no advantage, and in fact, very slightly worse between the two. So silver plating being the much harder process to get a PC board shop to do becomes the one you don't want to worry about, right? It just doesn't provide enough benefit or any benefit. And so you want to stick with the very conventional gold over nickel, which basically every PC shop under the sun can do. So definitely the way to go. And third, again, we had that idea that, well, maybe nickel is not a good solution, right? And if we're doing gold, we have to include nickel. And the way you don't do that is you just build copper and then you solder mask cover it. You don't want to leave the copper to oxidize outside. And so you basically are going to solder mask cover it. And the dielectric loss from the solder mask appears to be what's bringing this down and causing higher loss in this case. And then the strip line has higher loss, and you also see some roll off from vias. So basically all of that, the summary is, boy, your microstrip with the standard gold over nickel plating did great. That's where we should be to start with, right? That we're not seeing a winner beyond that. Now let's look at a little closer at the CPW versus the microstrip, right? We've already seen this is better than this, but let's double check that, do a different set of experiments, and look at, as we pull in this gap, how do things behave? We use 1x here to define this. 1x just means the trace width here is equal to the air gap here. And going out, there's a couple of literature quotes trying to find things on, again, the conventional wisdom out there. PCB fabrications issues have less impact on microstrip circuits than grounded coplanar waveguide circuits. That's kind of true. If you have over etch or under etch, because you've got more coupling here, you're going to see it twice as much as with the microstrip. Microstrip will be more resilient to any of those changes. And second, microstrip suffers increased circuit losses in the millimeter wave frequency range, making circuit technology less efficient for use at frequencies of 30 gigahertz and beyond. So I've heard this and I've yet to see it, right? All the data we've taken, it performing great as far out as the coplanar waveguide. So here's another set of examples. This is just looking at the coplanar waveguide as we pull it in closer and then go all the way out to where we just have a microstrip. And the purple here, pink, is the best performing. That's the microstrip. The coplanar waveguide 1x and the 0.75x are pretty indistinguishable from that. They basically overlap. And then as we get down to 0.5x and then 3 mil, we start to see some separation. The 3 mil looks worse because it's at the edge of our tolerances for the PCB. So the takeaway from this is that a coplanar waveguide of 0.75x tends to be where we see equal performance to the microstrip, but you get the shielding benefits of a coplanar waveguide. So this should be what you target in your design. That gets you the most density of signals for the best performance, right? That's the sweet spot that we see from this data. So 0.75x. So microstrip provides the lowest loss. Loosely coupled CPW is equal, of course, because you basically can decouple it enough that you're primarily looking like a microstrip. And the closer the CPW spacing is, the higher the transmission line losses. But CPW has the benefits of shielding, and so therefore it is preferred. And again, a lot of RF engineers are going to go in that direction. And so it's easier to convince them of a specific spacing than it is to try to say just use a microstrip, even if you felt you had enough space that the shielding wasn't an issue. Okay, we're going to look at some simulations versus measurements. This is kind of just to show what we can look at from the simulations I looked at originally versus the actual measured performance that we're getting. These are dialed in a little bit. So if we jump to the first one, we've dialed in our parameters so that they match what we measure. And the real question is, you know, as we remove the dialing and we just look at the exact same design or very similar designs, but with different dielectrics, is there one that stands out above the rest? Or again, are they all going to be basically what we looked at in the first simulation chart, which is everything groups together because they're all about the same. And whether you're buying a BMW or a Mercedes, you're getting a luxury car, and it's just not, you know, does it make a difference, right? Is what we really want to know. What's the reality of it? So this is MeteorWave 8000. This is Rogers 4003. We don't have the head-to-head comparison yet. We have a couple other dielectrics that we're very interested in looking at, and then putting them all on one chart and seeing how they perform, and, you know, giving us the data that we want and you guys want for looking at where the best performance is. All right, so conclusions. Trace simulations work pretty well to about 45 gigahertz where they start to deviate. That's looking here, right? We're starting to see some up to about here, then we start to see some noise rolling off in the plots where they start to deviate a little from our expected performance. CPW 0.75x is preferred, and gold over nickel is preferred, with no solder mask over the trace, right? Now, this is, let me make a quick comment here. It's very often extremely valuable to have what we call a solder mask dam by connectors or solder to keep solder from going down the trace. That seems to be pretty negligible, where you have a very short chunk of solder mask that goes over the trace, keeps solder from flowing down. It just acts as a barrier. and keeps you from having issues where you put too much solder on and you're getting solder down a trace. You're getting solder starvation at the joint because it's flowing down the trace, etc. So I think that's beneficial, but having large chunks of trace with solder mask over it is not if insertion loss is critical to your design. All right, this is my last slide. This really talks about the remaining questions out there, right? We've got a number of test boards that we were building, and unfortunately they were delayed. So I wasn't able to get this data and put it in this presentation, but in the next month or two, we should have all of this and answer these questions, which I think are really interesting. Again, what are the etching differences? Any peg, wrap plating. I think we've kind of answered wrap plating. So any peg is a really interesting one here. The dielectric comparison, and a couple we haven't talked about, which are the best via options. This is going to be sometime a lot later. And then the best connector options, which we've got test boards that have been built for this, looking at good connectors at different sizes, densities, through hole, surface mount, etc. Where do you find the choices are the best? All right, that's the end of my presentation. If there are any questions, I'd love to answer them.
Thank you, Dom. We have a lot of questions. We probably don't have enough time to answer them all. I just fire off right away. So I think your presentation spent a lot of time on the trace simulation measurement. There's a question on what about the components used on the board, such as balance, filters, switches, or even capacitor resistor? Are they all high precision, guaranteed performance?
No, absolutely not. Especially passives, resistors, inductors, capacitors. They do all have some parasitic behavior, and you do need to characterize them either with the manufacturer that is good enough that they provide a reliable, trustworthy touchstone model, or you need to measure them yourselves and get the performance, especially when you're doing the optimization or these high quality RF components. It's very important you have a good model for them. In terms of the balance and stuff like that, we've done simulations on those, but to begin with, we want to focus on kind of the fundamentals, right? Start at the bottom and work our way up. And I think getting to the starting point of the dielectric, the structures, the etch type, that is all the starting point we want to be at before we start saying, all right, now let's look at the functions that will affect the balance and modify the frequency range of the balance slightly, that type of thing.
Okay. I think a lot of folks in our audience don't like the 10% tolerance number you put there for microstrip. Probably your boss probably won't like it either.
Right. That was really set out as it's often what you see in the industry, where you go out and you try to get a microstrip, and the default answer from PCB shops tends to be 10%. We can do 5% on outer layer, but that's more the exception rather than the rule.
There's practical question is it possible to minimize tolerance using pilot production? So you basically have a pilot run, then you dial in number more precisely.
And that's typically what's done is you run a scout panel that goes first, and then you run some numbers on that, and you optimize it. Even for 5% impedance tolerances on inner layers, you do that. But there's still a lot of variables that go into it, right? And all of those operations are tolerances on your design, and they impact your ability, our ability as the manufacturers, to get the PC board to be consistent every single time, right? If you've got one step, you're just etching a 6-ounce inner layer copper, that's easy to dial in because you don't have a lot of tolerances going in there. There's your bath, there's the thickness from the manufacturer, which is very well controlled. But when you start going into this much more detailed process where there's a lot of tolerances that get added in, it's much more of a challenge.
So you mentioned a little bit different material have different property from the manufacturing perspective. Do you have, or does R&D Altanova has any preference on what the dielectric laminates to use based on the experience you guys have?
We do have our dielectric favorites, but a lot of that is due to, there's of course some supply lane management concerns, right? We tend to work with some of the dielectric suppliers that are domestic because our shop is in the US, and we don't tend to use some of the, we have a harder time getting material quickly from some of the overseas manufacturers. And so those concerns, while interesting for how do you get a product quickly, and how do we negotiate the best price on our side and have the best relationship with a supplier, those are all very important considerations from our perspective. But from the RF designer's perspective, if there is a dielectric which has a superior performance, then it doesn't matter. They want to use that dielectric, and that's a fair assessment. So our goal is to say, how do these dielectrics stack up? The ones we're using that we've used the most, so we have the most experience with, do they make the most sense? How do they compare against the competition? If they're better, great. That makes it really easy to sell that. If that's worse, then we have to be able to deal with, go out and get these other dielectrics and use them and have enough experience that we've got the inventory and stuff like that, so that when they're asked for, we can knock them out of the park.
I think we probably have only time for one more question. So let me ask you, I think folks noticed that the microstrip trace width is pretty wide on your presentation. Mm-hmm. So that the folks wondering, how do you deal with high density routing in that case? And also relate to the question, how do you, what's your strategy for breaking out the millimeter wave pins, which is inside the package for array?
So those are the ones where you typically will have to go to some sort of strip line. Many of the high-speed RF designs that we've dealt with have all their high-speed RF pins on the perimeter. That's probably like 60–70% of all the RF designs we've seen are that type of design, where you've got a couple high-speed RF, they're on the outside, you can fan out and go to this wider trace and it's not a problem. The ones where you cannot do that, then you're looking at dropping it into a strip line to get inside, because trying to route out between pads in an array is not desirable from an impedance standpoint, from a isolation standpoint, from a performance standpoint. So generally you'll go to strip line in those cases. And then when you're looking at the ones on the outside, you can generally fan out to get to the lower loss traces. What I did show is some very wide traces for RF, but we've used those in designs when maximum performance is required.
Thank you, Don.
To once again thank our sponsors who've made this event possible and made it available without registration charge to the attendees. Our premier sponsor, Cohu, our emeritus sponsor, JonsTech, our honored sponsors, ISC, iWin, and TSE. Our distinguished sponsors, Backer Hotwatt, Innovative Circuit Engineering, JMT, Nidec SVTCL, R&D Altanova, UI Green. And lastly, our exhibitor sponsors, ELES, MJC, Phoenix Test Arrays, and Smith's Interconnect. So I'd like to thank all of them, and also give an extra special shout out to Cohu, who is our premier sponsor, and they are the market leader in test interface solutions for very challenging applications in different areas. And also would like to thank ISC, who's the global #1 total test solution provider with products in the elastomer socket and interposers, spring pin socket solutions, and burn-in socket solutions. So once again, I thank all the sponsors. I thank you as the attendees. We look forward to seeing you again tomorrow at 7 a.m. Pacific time. I wish everybody a great day, so thank you.